A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Our first step in solving maximum-minimum problems is to draw a picture if necessary. So let's draw a picture of this situation. So here we have a straight river, and the farmer wants to create a rectangular field that borders this straight river. And we're interested in finding the dimensions. So the dimensions of a rectangle would be width and length. So we can label one side the width and then another side the length. So we are trying to figure out for what width W and what length L do we get maximum area. Now here's what we do know. We do know that the farmer has 2,400 feet of fencing. So we know total, this W plus L plus W will be a total of 2,400 feet. So writing that as an equation, we have 2W plus L equals 2,400. Now our goal is to maximize area. Here we're working with a rectangle. So the area of a rectangle then is width times length. We can use A for our function here for area. Now we need to write this function for area, the formula that we want to maximize. We want to write it in terms of one variable. So we can write it in terms of W or we can write it in terms of L. I'm going to choose to write this formula in terms of W. So here we have width times length. We need to get rid of length and write it in terms of W. Well, going back to what we know that 2W plus L gives us 2,400. So let's solve this for L. In doing that, we get L equals 2,400 minus 2W. So here we've expressed length in terms of W. So when we come up with our area function, we can write it in terms of just W. So here our area function is going to look like W, and instead of L, we're going to replace L with the 2,400 minus 2W. Alright, simplifying, we have our area function now looks like 2,400W minus 2W squared. Now this is the function that we want to maximize. We want to find the maximum of this. Well, maximums occur at critical values, so we need to find critical values of this function. So we need to take the derivative. So the derivative of this function is going to be 2,400 minus 4W. Now we need to set the derivative to 0 to find critical values. We want to know where is this derivative equal to 0. And since this derivative is defined for all x values, we don't have to worry about values for which it doesn't exist. So setting the derivative to 0, we have 2,400 minus 4W equal to 0. Solving for W, we have a negative 4W equal to a negative 2,400. Dividing both sides by a negative 4, we get that W is equal to 600. So we have one critical value. To verify that this critical value is in fact a maximum, we need to check it in the second derivative. So let's take the second derivative. The second derivative is going to be just a negative 4. So evaluating the second derivative at 600 then is equal to negative 4, which is less than 0. So since the second derivative is negative, we verify that this is in fact a maximum. So A of 600 is a maximum. So we know that having a width of 600, and in this case our dimensions here are feet, so having a width of 600 feet gives us a maximum area. Now we need to calculate what the length will be. Well, we know that the length is equal to 2,400 minus 2W. So our length then is going to look like 2,400 minus 2 times 600, which comes out to be 1200. So having a length of 1200 then creates the maximum area. So our dimensions then would look like a 600 feet by 1200 feet rectangle.